So we start exactly where we stopped yesterday with the last statement that the Allais manifolds are the hyperkähler quotient of a suitable C2 order of gamma flat manifold with respect to a suitable group. For this, I should only mention a couple of definitions that are standard in algebraic geometry about what means a crescent resolution. It is a rather strange name. It's discrepant minus 1. So something that is not discrepant, algebraic geometers call crescent. That in Italian sounds not so nice, but in English nothing thinks of bad things. So first of all, one should have clear the notion of canonical bundle. Canonical bundle is very trivial thing. Is simply the bundle of all. If you have a manifold, a complex manifold on that of dimension n, on that complex manifold you can consider the bundle of n, 0 forms, holomorphic forms of degree n. Obviously this bundle is a line bundle because there is only one dimension possible, and that bundle is called the canonical bundle. When the canonical bundle is trivial, we have what we call a Calabi-Yau manifold. Namely, there exists a globally defined omega n0 manifold. Now, when you have a singularity, you are always looking for resolution of the singularity. In algebraic geometry, this means that you have a morphism, so-called morphism, between the resolved variety, the variety that is supposed to be replacing the singular variety, by replacing the singular points with suitable P1s, and you say that this resolution, the morphism between the resolved variety that is not singular and the singular one, has the property that the canonical bundle of the two variety are isomorphic. You say that it is crescent if the canonical bundle of the singular variety and the canonical bundle of the resolved variety are isomorphic. That means in particular that if you are considering the most the simplest case of singularity, that is the case where you simply take Cn, the complex flat manifold with n dimension, and you create the singularity by quotienting this manifold with respect to the action of some discrete group. The discrete group will have some fixed point in its action, and that fixed point is the singularity. Now, the resolution is called crescent if the canonical bundle of W is equal to the canonical bundle of Cn over gamma, but the canonical bundle of Cn over gamma, which is, except for the singularity, 0. I mean, it is globally the Chern-Simon, the Chern classes of all of such a bundle is 0. Then also the chair class of the canonical bundle on W should be 0, and that is the definition of Calabi-Yau. So essentially, a crescent resolution of a Cn over gamma leads to a Calabi-Yau manifold, typically a non-compact Calabi-Yau manifold. So there is a very deep theorem. I think this theorem is something among the most exciting things I met in mathematics, and is still a theorem that has to be explored in many respects, because it is well established in the case n equal 2, and in n equal 3 the proof is already very complicated, and not all the examples are known, but it is claimed that works also in higher dimensions. And this theorem establishes a correlation between the cohomology, the double Bow cohomology of the resolved variety, and a completely group theoretical datum, that is the number of conjugacy classes of the group gamma, and something that is called the age. Let me define this concept of age, which is extremely simple to define. You suppose that you have a group gamma acting in a holomorphic way on the coordinates of Cn, so on a n-tuple of, you can hear me because there was some, okay. This does not work. Well, I will use this pointer. So C1, Cn are the coordinates of Cn, and every element of the discrete group is some matrix belonging to SLN that acts on these numbers. Since the group is finite, it means that gamma has an order, obviously, a finite order. So there is a power r such that gamma r is equal to power r is equal to 1. That means that the matrix can always be diagonalized, and it has eigenvalues that are of this form, necessarily. Now, what is important is to look at this number ai, defined modulo r, of course. And the age of the element gamma is defined in this way, is the sum of these eigenvalues, logarithm of eigenvalues. Obviously, the property of the age is a property of the entire conjugacy class, because all elements in the same conjugacy class have the same age, since the only thing that can happen is a permutation of the eigenvalues. So the theorem, which is of an extremely profound character, is the theorem that tells you that in the resolved variety, C3 over gamma or C2 over gamma, the dimension of the 2K cohomology group is equal to the number of conjugacy classes of age k. So there is this, obviously there is always conjugacy class of age 0, that is the identity, and and that is unique. This tells you that there is age 0, namely the constant. That is clear. Then people talk about junior classes. The junior classes are the classes where the age is 1. and the number of junior classes is equal to the dimension of H2. Then you have higher classes, classes of dimension 2, and that tells you what will be H4, and so on. Now, we can have a look at the situation from the point of view of group theory. And one very important result that was obtained no later than the beginning of the last century, well, 2 centuries before, actually, because it was, no, yes, last century, beginning of the 20th century, it was obtained before World War I, was the classification of all possible finite subgroups of SL3. We know the classification of the subgroups of SU2, and that is the IDE classification. A similar classification exists also for SU3. For SU4, we don't know already. The classification was done in the United States by 2 mathematicians whose name, I am honest, I always read because I have forgotten every time. I know only that they did this. And it is extremely simple. It tells you that the possible subgroup of SU3 are a series, some series of infinite series of solvable groups, and then there is a unique simple group that is L168. The simplest, it is very much similar to what happens in the case of SU2, because there the IDE classification tells us that we have tetrahedral, octahedral group, dihedral group, and cyclic groups. They are all solvable, but there is a unique simple group, and that is the icosahedral group, which is, by the way, the smallest simple group. In SU3, we find some solvable groups and a unique simple group that is the next smallest one, L168. So obviously we can use L168 and any of its subgroups. L168 has this structure. It contains 6 conjugacy classes, and obviously, since it has 6 conjugacy classes, has 6 irreducible representations. The irreducible representations are 1 of dimension 2 of dimension 3, 1 of dimension 6, 1 of dimension 7, and 1 of dimension 8. For interest for us are the representation of dimension 3 that are complex, and in fact the 2 representations are simply complex conjugate of each other. So we can calculate the age, and the age are this. We have 1 of index of H0, 4 of index 1 of H1, so 4 junior classes and 1 older class of H2. That means that if we take C3 over L168 and we make a Crepant resolution, we predict the cohomology of this manifold. The cohomology is that we will have 5 2 forms, 1 forms, and we will have 1 2,2 form. Okay, one group, the L168 has maximal subgroups of order 21 and or of order 24. The subgroup G21 is the subgroup, the maximal subgroup that contains elements of order 3 and 7. Actually, it is a semi-direct, from an abstract point of view, is a semi-direct product of Z3 with Z7. We can calculate the ages in the representation, three-dimensional representation, and we find 3 junior classes and 1 older class. So in this case, the resolution will tells you that there will be 3 1-1 forms and 1 2-2 forms. 2-2 form. In the case, so this was just to give you an idea of what more complicated can happen in the case of C3. But I will focus on the well-known case of C2 over gamma that now we will see corresponds to the Allen manifolds. Here we have this interesting table. Since we said that the possible subgroups of SU2 are just classified by the ADE classification, we have the cyclic groups, the dihedral groups, the E6 that corresponds to tetrahedral, E7 octahedral, and E8 icosahedral. Now you see on this line what I call W gamma. This is Arnold classification of singularities, which from this point of view is extremely simple. What is it? Let me show you, for instance, how you derive the first singularity. In the case of cyclic group. In the case of cyclic group, you have an action on Z1 and Z2. Okay? This is the unique generator of the ZK group on this. It is very easy to see what are the invariants with respect to the action of this guy. Clearly, if I take Z1 to power k, this is an invariant with to the group. I have, let me call this invariant U. Then I call the invariant W is Z2 to power k, obviously. But another invariant that I will call Z is Z1 times Z2, because obviously the product of these two phases. So you see that there are 3 invariants of the group, but they are not independent. Obviously, they satisfy the equation that Z power k is equal to U times W. Okay? Now, you can change this equation by redefining U as equal to A plus B and W as A minus B. And this will be written as A square minus B square, obviously. Right? So now you see that I can describe the orbifold C2 over gamma as a locus in C3, because this equation, which is identically satisfied by the invariants, is a description of the singular variety. there is a one-to-one correspondence between the points in C2 that are invariant, I mean the equivalence classes of points in C2 with respect to gamma, and the locus in C3 of points that satisfy this equation. This is, if you extend the same procedure to the other groups, you find this other polynomial that describe, therefore, the singular locus. Now, these are the polynomials that Arnold classified within catastrophe theory as the singular, the possible singularities. The one-to-one correspondence between the simple singularities and these orbifolds. Now, what is that you can do? Now, you can deform these singularities by adding what in, for instance, conformal field theories is called the chiral ring. Namely, you consider the ring of polynomials in three variables, u, w, and z, modulus the so-called vanishing relation, namely the polynomials that are obtained by the derivatives of w, written here, with respect to the three coordinates. This chiral ring is a finite ring of polynomials, and you can deform this polynomial here by adding the subleading polynomials obtained in this way. Here I mentioned the subleading polynomials. And the dimension now of this chiral ring is k, k plus 2, 6, 7, 8, and etc. And you will immediately see that this dimension of the chiral ring is equal to the rank of the corresponding Lie algebra. In the on the other hand, the number of conjugacy classes of the group is 1 plus this dimension of the chiral ring. Now, from the point of view of algebraic geometry, the resolution of the singularity is the affine variety, namely the zero of the polynomial, obtained by deforming the original polynomial with some parameters, with the linear combinations of polynomial in the chiral ring. And these parameters, of course, are as many as the chiral ring. Now, this procedure can be now understood as a Kähler quotient, hyper-Kähler quotient. Let's see how we do it. And this is what I'm going to tell you. Here's the heart of the McKay correspondence and of the Cronomer construction. So let's first of all observe this fantastic correspondence that was observed by McKay. McKay is a Scottish mathematician, still alive, living in the United States or in Canada. I have forgotten if, I think it's the United States, who has had in his life this incredible capacity, ability to see relation among things that are completely different and no one else sees. The first in history has been this correspondence between Dinking diagrams and, as you will see, the composition of irreducible representation of the SU2 subgroups. Another thing that it was the only one to see is even less evident to all the others is a relation between the irreducible representation of the so-called monster group, the largest simple group, and the coefficients in the decomposition of a certain modular form. And that was the beginning of what was later realized to be the relation between the monster group and the moonshine lattice, also relevant for bosonic group theory. So he is incredible. He has an intuition for things that no one else sees. So let's see what is the McKay correspondence. Okay, you can address a very simple problem. You have any representation of a group can be decomposed into irreducible representations, as we said in the first lecture. Now we consider in particular the Q representation. That is the, in this case, is the defining SU2 representation, 2 dimension, which actually is also always an irreducible representation, but it is not important that it is irreducible. It is the representation that is relevant for the action on C2. And you multiply this representation by d mu, which is any of the irreducible representation. This tensor product, of course, can be decomposed into irreducible representation. And in this way, you define a matrix A mu nu, made of integers, of course, because these are the multiplicity of the irreducible representations. Now, the fact that McKays observed is that if you define 2 times delta mu nu minus this matrix, what you obtain is the Cartan matrix of the affine extension of the corresponding Lie algebra. So a complete new quality in the correspondence, in ADE correspondence. So far, we had only discovered that the same Diophantine equations is at the origin of the classification of the groups and of the Lie algebras. It was an interesting coincidence, but the relation between the Dinking diagram of the algebra and the group was by no means evident, and you might suspect there is no relation. Instead, the Dinking diagram contains an incredible information about the Lie algebra. In fact, what happens is that, we will see in the next transparencies, the Coxeter number are just the dimension of the irreducible representations. Let me show what happens. The affine Dinking diagrams are the Dinking diagrams of the corresponding Kac-Moody algebras. Every finite Lie algebras admits an extension to a Kac-Moody algebra, and the corresponding Dinking diagram is obtained in a very simple way. You add a dot to the Dinking diagram, which is black, and simply represents the highest root. Every algebra has a well-defined highest root. The highest root has components along the simple roots that are integers, and these components are called Coxeter numbers. So you simply add the black dot, and then following the rules for Dinking diagrams, you obtain these extended diagrams. Now what happens? What happens is that the corresponding Cartan matrix of the extended Dinking diagram is precisely what I told you in the previous transparencies. Is 2 times delta mu nu minus A mu nu, which is defined by the decomposition. And now what happens is, therefore, that this extra dot, I mean every dot from the group theory point of view, corresponds to an irreducible representation. And the extra dot is just the identity representation that is always there. And there is associated a number. The number is the Coxeter number, namely the components of the highest truth with respect to that irreducible representation. But what you see is that these dots, this number associated to the dots, are precisely the the dimension of the irreducible representation of the considered group. So this is the fantastic Coxeter identity of Coxeter numbers with dimensions of irreps, and it is the fantastic McKay correspondence that now in higher dimension as an extension to more complicated diagrams that are not anymore Dinking diagrams of any Lie algebra. Relying on this McKay correspondence, we can construct we can address the Cronomer construction. Cronomer construction works in the following way. Mathematicians are interested in this space, P, that in mathematical language is described as the space of homomorphism between the regular representation of the group and the tensor product of the defining representation Q with the regular representation. What does it mean in simple man language? It means that a regular representation, I remind you, is the representation that has the same dimension as the order of the finite group. Namely, to every group element you associate a vector, unit vector, and then the matrices, essentially the matrices are just given by the multiplication table. So the regular representation is the representation that if you associate a unit vector to every group element, the action of R gamma on ED is just E of gamma times D. This is the regular representation. So you introduce a vector of two matrices, in this case, a vector of two matrices. And each matrix is a matrix in dimension equal to the regular representation. So you have constructed a space now that has dimension gamma squared, order of gamma squared, times 2. Okay? And on this space, now you define the action of the group. The Q representation is given by a matrix of this type. For each element gamma of the considered group, of the considered finite group, you have a 2 by 2 matrix that is SU2 matrix, so it has necessarily this form. And you have a regular representation matrix. So you conjugate the two matrices A and B with R, and then on the result you apply the 2 by 2 representation. Okay? So this is the space P. And on the space P we have defined the action of gamma. Now we go to the space S, which is the submanifold made by those points in P that are gamma invariant. Gamma invariant means that these two matrices are mapped by this action in the same matrices. If you like, the condition on the matrices, the doublet of matrices belonging to S, is that they behave in this way. Such a space is called S, or in mathematical notation is called homomorphism index gamma of R times Q. in Q times R. Okay? You may think that solving this constraint, this is a constraint on the entries of A and B, might be a very difficult thing. Actually, it is not, just because of the McKay correspondence. We can immediately predict the dimension of the space S. The reason is that we utilize McKay correspondence and Schur's lemma. Due to McKay, we can decompose Q times R into irreducible representation, and we decompose R in irreducible representation as well. And due to Schur's lemma, there can be a non-trivial homomorphism only between identical representations. So, using McKay correspondence, we see that we have homomorphism between CNM and Cn weighted with the matrix A mu nu, which is the McKay matrix. Now, the McKay matrix has a very important property. We just saw that the eigenvalues of the McKay matrix are 2 times the dimension of the irreducible representation. So using that, we find that the dimension of S is just 2 times mu times the dimensions of the representation mu squared. And this, as we know, is the order of the group. So the dimension of this space S that we have constructed is exactly 2 times the order of gamma. This manifold, made of matrices that satisfy the constraint, actually is a hyperkähler manifold, a flat hyperkähler manifold. Given this doublet that I call P, the trace of the differential of P, dagger, wedge P, dP, is a doublet of matrices that I can identify with the Kähler matrix on the diagonal, decomposing along sigma matrices, and with omega, which is the holomorphic form of the hyperkähler manifold. I can write, therefore, very easily, explicitly, the Kähler metric. The Kähler metric is this thing, is the trace of the A dagger, wedge dA plus dB dagger B. And the form and the holomorphic part is just a trace of dA wedge dB. So this is the space of which now we are going to take the Kähler quotient with respect to a suitable group. What is the suitable group? The suitable group is the normalizer. Well, just before doing that, I show you for AK how we can explicitly solve the constraint. This is the way to solve the constraint explicitly. We go to the basis where the regular representation is diagonal, namely it is split into irreducible representation that for AK are all one-dimensional. And there it is very easy to solve explicitly the constraint. And so you find that the matrices in that regular representation, the matrices satisfying the constraint and filling up the space S, are given by these matrices that depend, as you see, on K complex number U, and this on K complex number nu. So here you see explicitly the coordinates of the 2 order of K dimensional space we mentioned before. For non-abelian groups, the resolution of the constraint, the explicit resolution of the constraint is more laborious, but can be done. And now, what is what I call the gauge group? I call gauge group the group with respect to which you will take the hyperkähler quotient. It is simple. It is the group that commutes the subgroup of SU gamma that commutes with the action of gamma. We can think of our matrices as a doublet, or if you prefer, we can look at them as the elements of a quaternion. Namely, we can arrange them in a 2 by 2 matrix. I mean, A, I, B, dagger, I, B, A, dagger. And the transformation with respect to an element of SU order of gamma is simply conjugation of each of the matrices. Well, there is nothing more than that. Now, we look for those, for that subgroup of SU gamma, which keeps the subspace S invariant. And this happens only if this action commutes with the action of the discrete group. Then, once again, it is very easy to see what this group is. There is a UN for each irreducible representation. So, in general, this group is the tensor product of as many U in dimension nm and mu, where n mu is the dimension of the mu irreducible representation, intersection with SU gamma. This simply means that there is an overall phase that you do not consider among all the U's. This means that now the dimension of this group is easily obtained. The dimension is of U and mu, the real dimension, is certainly n square minus 1. Sorry, it's obviously n square. So the sum of n square, but there is an overall phase that you discard, so it's minus 1. That means that the dimension of the group F is order of gamma minus 1. And now we can remind ourselves of the Kähler quotient procedure I described in general terms in yesterday's lecture. You remember that for each generator of the group, I subtract 4 times I subtract a 4, because 3 are the constraints from the momentum map, and 1 is the quotient with respect to the group. So the dimension of MZ is the dimension of this space. Now I'm looking at real dimension. The dimension of this space was complex dimension 2 order of gamma. So real dimension is 4 gamma, and to that I subtract 4 times gamma minus 1. But that means I subtract 4 gamma minus 1 from 4 gamma, and the result is always 4. So whatever, here the bracket is not properly placed, is here. So whatever you choose, whatever is the group you consider, the Kähler quotient will construct a larger, you will construct a larger space, but you will have a larger group, and the difference in the Kähler quotient will always be 4. So you construct a series of 4-dimensional manifolds that are all hyperkähler by construction. we claim that these manifolds are the resolution of the C2 singularity and the Hale manifolds. This was the really profound result of the two papers produced by Cronomer in 1989. It's a result of 1989. In mathematics was really a breakthrough. So we can just look at the explicit form of the moment maps in the case of AK. The moment maps are constructed according to what we discussed in general yesterday, and they turn out to be very simple. The group now is simply a product of U1s, but you discard the overall U1. So the matrix is of this type with the condition that the sum of all the phases is 0. And if we call F each of these generators corresponding, you can use, for instance, the gauge where you take F0, F1, and Fk is the sum of all the others, minus the sum of all the others. So the moment map is simply the trace of A commutator A dagger, or B commutator B dagger with Fa. For the the real part of the, we have a triplet. We have to construct a triplet. We decide that the Keller form is the third one, and we take the linear combination K1, sorry, it's K3. And we take K1 plus IK2 to be the complex. K1 minus IK2 to be the complex, the other complex. So we have a moment map that is the real moment map and the holomorphic. And explicitly, this is the result in terms of these coordinates u and nu that we introduced by solving explicitly the constraint, the invariance constraint. Given this, we can now see explicitly a realization of the final space, choosing the simplest case where k is equal to 2. This will be the celebrated Eguchi-Anson metric, introduced in not in 1989, but just 10 years before, in 1979. The paper by Toro Eguchi and Andrew Anson was written in SLAC laboratory in 1979. So they did not know anything at the time about a Keller quotient, and they constructed their metric directly. The way to construct the Eguchi-Anson metric is quite simple. You consider polar coordinates in 4 dimensions. So you have 3 angles, theta, psi, and phi, and you introduce 3 one-forms that satisfy the Cartan-Maurer equation of the SU2 group, right? So these 3 forms you can check the realization of this exterior algebra. The derivative of each of these guys is equal to the product, the wedge product of the remaining 2. Okay? And if you take the metric that is dr squared plus r squared times the sum square of these forms, you simply write the flat metric in 4 dimensions in terms of polar coordinates. The Eguchi-Anson metric was obtained by writing the following ansatz. You introduce this very simple function, w of r, that is 1 minus some parameter a over r squared, and you write this metric here. You see that if a is equal to 0, this is just the flat metric, because w becomes 1, and this is dr squared plus r squared, sigma 1 plus sigma 2 squared plus sigma 3 squared. This is the flat metric in 4 dimension, in Euclidean 4 dimension. But you see also another thing. You see that for r very large with respect to a, this is essentially the flat metric, because for r very large, w is almost 1, and this is the flat metric. So this is an asymptotically Euclidean metric, at least locally Euclidean. Because the important thing to note, and it was noted by Eguchi and Anson, is that actually when you go at very large r, this metric admits a symmetry, that is identifications of points with respect to a Z2. So actually, local at very large R, what you see is that you do not have the sphere. You do not have the 3 sphere as you would have in a really Euclidean space. But you have the 3 sphere with antipodal points identified, and that is the Z2 symmetry. So it is only locally Euclidean, not globally Euclidean, because of that. Now, let's see how this metric can be retrieved, first of all, as a Kähler metric. It is not obvious that what we wrote there, that what Anson and Eguchi wrote, is actually a Kähler metric in a 2-complex dimensional manifold. The way to see it is a rather sophisticated transformation of coordinates. We introduce 2 coordinates, 2 complex coordinates that are given here, Z1 and Z2. You cannot see by just by intuition. You have to know how to do it. And you have to do it, it's a long calculation. If you introduce this 2 combination of G rho, that is rho, the 4th root of rho 4 to the power 4 minus 1, with these phases, then what you can verify is that the following metric, defined as d bar with respect to this coordinate, of the following Kähler potential. You see it is a complicated function. It is, let me call tau, the sum of the 2 modulus squares. Then if you take the square root of tau square plus 1 minus the logarithm of this plus the logarithm of tau, and you take the derivatives of dz and d bar, and you multiply by dzi bar, you obtain a metric. And this metric, by replacing at the end this substitution, produces exactly the Eguchi answer. So this is something that shows that the Eguchi answer metric is Kählerian, because I'm able to find a basis of complex coordinates and to identify the scalar potential. The next point is to realize that this scalar potential and this metric, therefore, can be obtained as a suitable scalar quotient, as a scalar quotient in the Cronomer construction. Let me show it. Relation with the Cronomer approach. If I take the case k equal 2, the moment maps are given here. Okay? And where I have introduced the u and the nu defined before. Now let me change the coordinates in this approach, in this writing. Let me introduce a doublet that is u0 and nu1, and a second doublet that is nu0 and nu1. Then rewrite, this is rather simple thing, rewriting the moment maps in terms of the u coordinates, you find something much more appealing. You find that this is the sum of the u square minus the sum of the v squared, and the holomorphic part is simply ui times vi. Now, the next point is to realize what I told you before. This is, in the previous lecture, complexification of the gauge group. Here, the gauge group is simply U1, because we said that is an order of the group minus 1. So the order of the group is 2. I have only one U1. I complexify U1, and I obtain what? I obtain the real part is just dilatation transformation. So the U1 transformation on the why I did it in this way, because the transformation on U and V are simply the phase EI phi and minus EI phi. Complexifying means that I make the transformation E times bold phase V, and the other with the opposite weight. The fundamental observation, which is general, is that under the complexified group, the holomorphic part of the constraint is invariant. This part is invariant, obviously, because there are opposite weights. Whether this is complex, whether this is the original group, or if I have extended it to the complexified form. So this constraint is invariant. On the other hand, this constraint is not invariant. Is invariant under the original part, but it's not invariant with respect to V. So now what I obtain is that I can define a transformation E minus V, EV, that changes the level. I had level 0. By means of a transformation of this type, I can change the level. And the strategy, therefore, to obtain the final result is that of choosing, by means of this transformation, I can make a gauge fixing. Namely, by means of this transformation, I can put U1 equal to 2, for instance. So I start from a configuration where U1 and U2 and V2 are equal, and I call respectively this Z1, while U2 V1 I call the new coordinate Z2. And now I obtain, starting from this configuration, a configuration where the level is L by means of a parameter of the complexified group that is given by this. This is a solution of an algebraic equation. So using now the general formula for the potential of the quotient, you start with the potential of the quotient at level 0. Sorry, of the potential of the potential restricted to the hypersurface of level L, that is this, and you obtain this term, minus L times the log of the transformation, I mean, that V, and this is this. Now, we see that for L equal 1, the scalar potential is exactly the scalar potential we obtained before for a Gucci-Anson. Obviously, the value L, only L equals 0 and L equals 1 are relevant, because any other value can be reabsorbed in a rescaling of the coordinates. So this is the quite laborious demonstration, proof, that the Kähler quotient a la Cronomer produces the Gucci-Anson metric. And this is the simplest case. From this you can, from the complexity of this simplest case, you can guess how much more difficult it is to do explicitly the higher cases. But what is important is the general proof that this is the classification of Halley manifolds. They are all Kähler quotient. Why is this so much important for the ADS CFT correspondence? I tell you in a moment, going back to what we have seen. We have a space S which is flat, okay? So, if you have a singularity, if you have some brane that is placed in some space-time, 10-dimensional or 11-dimensional space-time, and the transverse space to the brane, is a C2 singularity, or a C3 singularity. Then the question is how to construct the dual conformal field theory on the boundary. The Cronomer construction gives you precisely the way to do it, because it tells you that now you are going to describe the singularity and its resolution in terms of a hyper-Kähler quotient or a Kähler quotient. And you, in this way, have identified a much bigger space, the space S, which will be the space of scalar field in the dual conformal field theory. And the kinetic term of these guys will be the standard kinetic term. So this will be a renormalizable theory to start with, because the kinetic term is the standard one. It's just flat. But then there will be a gauge group. And the gauge group is precisely told you by the Cronomer procedure that can be generalized to. That tells you exactly what is the gauge group. And now, by using our law about supersymmetric field theories, we exactly know that the momentum map that we construct here explicitly is the ingredient that occurs in the construction, in the gauging of this model. I mean, it means that these fields are charged in the way we have seen with respect to this gauge group. Every field now is extended to a supermultiplet. It will be matter multiplets and whatever. And in a supersymmetric way, the transformation rules of the fermions in this theory will be dictated by these momentum maps that we know how to construct. And the potential, final potential of this theory will be given by an expression in terms of this momentum map. The levels will be the Fayet-Iliopoulos terms, as we said, and you have the entire construction. Now, what you see? You see that the vacua of the conformal field theory, well, the would-be conformal field theory that you have constructed, are just the resolution of the singularity. If the Fayet-Iliopoulos terms are 0, you just describe the singular case. And so the correspondence is the following. The geometry of the transverse space is the geometry of the vacua of the manifold of the vacua of the conformal field theory. The extra point that occurs when you go quantum is to make the theory really conformal at the quantum level. And that last step is obtained by promoting each of the C, each of the scalar field, with extra color indices. Namely, the gauge group, instead of being simply what we said here, take the easiest case is the case of ZK, where all the gauge factors in the gauge group was a product of U1s. Now this U1 is promoted to be a UN times a UN bar, because these fields are assigned to typically to a B-fundamental representation. Okay, B-fundamental representation. And this is the way it is done, for instance, ABGM. ABGM theory is completely contained in this approach with a ZK symmetry, with a abelian symmetry. The question that, to my knowledge, is not yet solved, and it is something that should be the object of study, is to understand this last step when we take the quotient with respect to a non-abelian discrete group. This is open field. As far as I know, no one has found the solution. And I would even say that no one has really addressed the problem. So this, in my opinion, is a very interesting field of new research. And it is entirely based on this geometrical engineering. Okay. I have still half an hour. And in this, essentially half an hour, right? Around half an hour time, right? In this last part, I would like to give you some ideas about the C-map and the C-star map that are very interesting constructions, geometrical construction, motivated, actually brought to existence by supersymmetry and supergravity, that instruct you how to obtain non-trivial quaternionic Kähler manifolds starting from special Kähler manifolds. So, but there are two versions. One version is very useful for to understand the cosmological models, and the other version that I call the C-star map is instead very useful to understand the construction, or to understand and master the construction of black hole solutions in supergravity. The two maps will be understood just simply by a change of sign. There is just a change of sign. So let us start with the more classical C map. The C map is a map from a spatial Kähler manifold of dimension n to a map to a quaternionic Kähler manifold of dimension 4n plus 4. And it is a universal construction that, starting from an arbitrary spatial Kähler manifold, gives an image manifold of this type. So if it is universal, it means that we can describe it in general terms, that there is a universal formula that we can write. The universal formula is contained. Historically, this map was started by a paper by Sergio Ferrara and an Indian student of UCLA of those years by the name of Sabharwal. But the way they did it is very complicated and obscure. They obtained the construction, but it is difficult to understand the general setup. The general setup now can be understood in a recipe that I'm going to give, which, by the way, provides the general form for the SU2 bundle. We know that the the quaternionic Kähler is critically connected to the existence of a non-trivial SU2 bundle whose curvature are the Kähler forms. So in this construction, it should be clear how to construct the SU2 bundle. This general formula did not exist, at least was, if you like, implicitly contained in the paper of Sabharwal and Ferrara of the beginning of the 80s, but was never explicitly given in other papers. These results are rather, in this form, are rather recent and were obtained in a collaboration by myself, Alexander Sorin from Dubna, and Mario Trigante in Torino. We published it in 2014. And moreover, this construction is absolutely online, and suitable to understand with the change of sign the other construction that we call the C-star map, that provides a pseudo-quaternionic manifold where the connection, instead of being SU2, is actually SU11, changes and gives Lorentzian manifold instead of Euclidean manifolds. But it's very important for black hole physics. So let me give this general definition. You start with a special Kähler manifold. Therefore, you have n complex coordinates. To this n complex coordinates, you have to add new coordinates in order to make a total of 4n plus 4 real coordinates. So these n complex coordinates are obviously 2n real. We need other 2n plus 4 real. The 2n plus 4 real are provided here. We introduce some coordinates z that are in number 2n plus 2, and that are indices exactly mimicking the indices of the symplectic bundle that by definition of special Kähler geometry exists on the bundle, on the special Kähler manifold. In addition, you add these two real coordinates, u and a. When the sign will be chosen in the way that corresponds to black hole physics, u and a will be related to the radial coordinate of the black hole, u, and a will be related to an extra coordinate that is called the Taubnat coordinate. In the pure case, purely Euclidean case, instead you can think of u and a as related to the time Euclideanized time of a cosmological solution. But I don't want to go into these details of physical interpretation. I want to stand on a purely mathematical I want to stand on a purely mathematical ground. So I simply mention what are the additional coordinates that you add to the coordinates of the special Kähler manifold, and then I will write down the metric. The essential items in order to construct such a metric is this matrix M4 minus 1. That is a matrix in dimension 2n plus 2 that is constructed starting from the matrix n, script n. We emphasize that this is fundamental matrix associated with the special Kähler geometry. Every special Kähler manifold involves such an object. And moreover, as a very important interpretation, as the gauge coupling matrix is the matrix that occurs in the Lagrangian in the kinetic part of the gauge fields, Lagrangian. But don't worry about that interpretation, just take this matrix as granted. This matrix we will see as very well defined transformation under any group of isometries of the special Kähler manifold. Then the metric of the quaternionic manifold, whose local coordinates are those that I mentioned, is given below. It is du squared. Then there is the metric of the original special Kähler manifold. Then there is this very special metric, very special type of contribution from dA, where C is the symplectic matrix in 2n dimension. And then there is this contribution here, if you like, the kinetic metric of the Z's, that is given by this metric M4 minus 1. Okay? I can immediately tell you that the only difference, this is quaternionic, and it is a positive definite metric, because if you look precisely at this metric, you see that this is a negative definite metric. If you put a plus here, you obtain the C star map instead of the C map. So, the question now is to see that the metric I have defined is indeed an hyper-Kähler metric, a quaternionic metric. So I have to construct explicitly the SU2 connection and the three Kähler forms. And I'll provide in the next transparencies the recipe. Very, very beautiful geometrical construction. So, in order to construct this general recipe, let me introduce some notation. I use some renormalized gamma matrices here. These are just the Pauli matrices, but I need to normalize them in this way for convenience. Next, I introduce the shorthand notation for this differential form. Given these preliminaries, I can tell you precisely what is the SU2 connection, omega, and what are the Kähler forms. The SU2 connection, as you see, involves the Q connection, or the original Kähler connection, the connection on the line bundle whose first term class is the Kähler class of the special Kähler manifold. But this is dressed with the new form phi, and then of course this is extended to be a SU2 connection by means of these objects, where these objects, I remind you that V is the object V we introduced in special Kähler geometry, is the holomorphic, covariantly holomorphic section of special Kähler geometry. So whatever is the Kähler geometry, I know, special Kähler geometry, I know what is V, and I know what is Q, and I know what is phi. And in terms of this guy, I can write this formula. The result for the Kähler forms, which is d omega plus omega wedge omega, is given here, the general result, and I have explicitly written here the objects in terms of some shorthands that are given here, ds and ds bar. So dv is the covariant derivative of the holomorphic, the covariantly holomorphic section of special geometry, and everything is defined. So it is absolutely, I mean, it's of some outstanding beauty, this formula, because it gives you the geometry of a quaternionic Kähler manifold completely in terms of the special Kähler geometry. So it's the universality of this map that is contained here. It works for special Kähler manifolds that are non-homogeneous, and for special Kähler manifolds that are homogeneous. The fantastic thing is that when the original special Kähler manifold was a symmetric space, the result of this formula is another symmetric space, known in the tables. We also have C-map and triholomorphic maps. Now we are, of course, in a position with this formula to calculate the moment maps of all the isometries. And there are three types of isometries in these manifolds, because all the isometries of the special Kähler manifold are isometries also of the new manifold. But the new manifold has always some isometries, even if the special Kähler manifold had no isometries. Why? This is obvious from this formula. First of all, you see that there is always an isometry corresponding to shifting A, because small a appears only under derivative. So there is a translation isometry of A. And since the coordinate z appear only in this way, a shift of z it's almost an isometry. Almost, why almost? Because this term does not depend on any constant shift of z. Here, however, it depends. But what we can do is always compensate such a transformation by a shift of A, a suitable shift of A proportional to the z's. That means that the algebra of the shift in z's and in A actually is not an abelian algebra, but is just an Heisenberg algebra. And all these manifolds have an isometry associated with an Heisenberg group. This is always there. All quaternionic manifolds in the image of the C-map have, by a construction that was not obvious to Sergio and Sabarval, because they were not writing the metrics in this way, the metric in this way, but in this way it is evident that there is always an Heisenberg algebra of isometries. These isometries are more, they come together with other isometries that are the original isometries of the special Kähler manifold. And when this original special Kähler manifold was a symmetric space, all these isometries mixed together in a larger non-abelian group and make a symmetric space. So I just go in a quick way through the further steps, and I tell you these are the Heisenberg. This is the Heisenberg algebra, and I will have no time today to discuss in details the Tizza-Take projection, because I needed one lecture more to arrive to that, but a little bit of introduction was given to you in previous lectures. Let us simply look at the result in this table. According to what we said in other lectures, the Tizza-Take projection corresponds to the fact that we can group supergravity models into universality classes by discarding the imaginary roots. Now, what is extremely useful and important is that now we combine the Tizza-Take projection with what I described to you, the C-map, because the most important property that I have no time to discuss in detail is that the C-map and also its non-Lorentzian version, the C-star map, commute with the Tizza-Take projection. So the Tizza-Take projection of the C-map image is the image of the Tizza-Take, of the C-map of the Tizza-Take projection. This is what gives rise to this extremely nice and compact table where essentially all supergravity models, n equal 2 supergravity models, are codified, because we have the list on the left of all possible special Kähler manifolds that are symmetric spaces. These manifolds were classified by Cronomer and Julian, not Cronomer and Julian, Cronomer and Van Prooyen in 1985, I think, or 84. But these models now are have a counterpart that is the quaternionic image. And there are also symmetric spaces, and they are mentioned here. As you see, we have 1, 2, 3, 4, 5, 6, 7, 8 models, where, however, there are 2 infinite families of models, depending on the number p. Correspondingly, here we have the image. This is the quaternionic image. And the quaternionic manifolds are those that describe hypermultiplets. And the C-map is very relevant for mirror symmetry, because it is in mirror symmetry you exchange the role of vector multiplets and hypermultiplets. And at the basis of this there is the C-map. But these infinite models, actually, I mean, this 1, 2, 3, set 4, 5, 6, 7, 8, 9 models. These 9 models actually are grouped in only 5 universality classes, where no one is infinite series, because the entire Tizataake projection of these manifolds here is SO5 4. There is an F4 represents all these guys. All these guys have the same Tizataake projection. So in the construction of black hole solutions, for instance, or in the construction of cosmological models, what counts and essentially what displays the main features of the model is only the Tizataake submanifold. The rest is just a little bit of dressing. And this dressing can be essentially modded out. So that means that as far as symmetric spaces are concerned, we have only essentially 5 models for n equal 2 and d equal 4. And there is always a relation between the quaternionic, namely the hypermultiplets, and the vector multiplets for mirror symmetry, by quote-unquote mirror symmetry. So I have no time to, and I will not address because the details are rather complicated, but I hope to have given you an idea of, first of all, there are new visions also in classical Lie algebra theory, like that is 1 century old, that are due to supersymmetries. This pairing of F4 with SP6, for instance, no mathematician ever considered it. I had no idea that they are relatives, because he had not any idea of the C-map. This is just one example. Secondly, the Tizataake was constructed in mathematics by Titz and Satake, but they made a very moderate use and did not know the relevance of this, for instance, for the construction of explicit solutions of supergravity models. At the same time, I tried to emphasize the relevance of the Kähler quotient and hyper-Kähler quotient construction. And I tried to emphasize that once again, although this is nowadays an ubiquitous technique in algebraic geometry for the construction of new manifold, could not even be deemed of without supersymmetric gauge theories. It comes from there. So all my conclusion is the same as at the beginning. Although these topics of advanced theoretical physics have borrowed a lot of knowledge from mathematics, we are even with mathematicians, because we have given back to mathematicians a lot of new ideas, of new conceptions, and to be really honest, some of this mathematics has not yet been duly explored by mathematicians. They should classify more of what we proposed. And the relevance of these constructions also for the ADS-CFT correspondence, which is, as I have seen listening to your gong show, is very widespread among your thesis work. I tried to emphasize that the geometrical picture behind it, which is group theoretical from many points of view, is very important. I mean, that this ADS-CFT owes a lot to these geometrical constructions. So my task was to tell you how relevant group theory is for all what you do, and moreover how group theory, the algebras and so on can be used in a modern way. I hope I have succeeded in this task.